Okay everyone, so in this video we'll be defining acids and bases. Now in this video we'll be covering 2 out of the 3 of them, and the first one happens to be the Arrhenius definition. So what if you were to define an acid as a producer of hydrogen ions and a base as a hydroxide ion producer? Turns out you'd be correct. You'd be partially correct. It's one of the definitions. And what good is knowing it if you can't really apply it? So, let's say we have hydrochloric acid, and we want to know what will happen to it. So, hydrochloric acid is one of the 6 strongest acids, and because of that fact, what does it mean exactly? It simply means that the acid will dissociate fully, and we get 2 ions. And because of that, we know that hydrochloric acid is an acid based on the Arrhenius definition. Now, hydrogen chloride, we know it's a covalent compound and it doesn't possess any ions. However, what happens when it interacts with water? What do we do with that? So, let's say we have 1 hydrogen ion. My bad. Let's say we have 1 hydrogen ion and it was to react with H2O. And don't forget to put in your phases. What is bound to happen here? So we know that H2O has 1 lone pair, and they actually consolidate to create H3O+. The H3O+ is known as a hydronium ion, and in water, hydrogen ions always associate with water molecules to form the hydronium ions and other associated species with the general formula where we have H and H2O and plus. That's usually the general formula for the production of hydronium ions and other associated species. Now, what happens if we're dealing with the base? What would that look like exactly? And one example would be incorporating sodium hydroxide. Now, using the Arrhenius definition, how do we analyze it? What's going to happen? Well, sodium hydroxide is one of the strongest bases, and if we were to break it down, right, we get sodium plus, and we get a hydroxide group. Now, what does it mean when a substance dissociates and it leaves off a hydroxide group or produces a hydroxide ion? But based on the Arrhenius definition, this would imply or confirm that sodium hydroxide is indeed a base. Okay, now let's say I was to deal with another reaction where I have 1 hydrogen ion and I was to have it react with, let's see here, a hydroxide ion. What would that look like? And it turns out that acids and bases naturally combine to form water. And it just simply means that under the Arrhenius definition, acids and bases tend to have the tendency to neutralize each other. And as a result, water becomes the standard byproduct. So we've covered the Arrhenius definition. Now let's move on to the other definition. So the other definition is known as the Bronsted-Lowry definition, and it's the same format as the Arrhenius definition, except there's a difference. Can you think of an alternative definition for acids and bases under this context? Turns out that the acid would simply be a proton donor, and the base would be the proton acceptor. By the way, we write H plus as protons because if you look at the periodic table, the proton is the same ratio as an electron. So chemists will use protons and hydrogen ions interchangeably. But I digress and return to our definition. So under this definition, how are we able to define, let's say, hydrochloric acid? If we have hydrochloric acid and it was to react with water, under the Bronsted-Lowry definition, how will that turn out? Well, let's define some things. Which one's the proton donor? And which one's the proton acceptor? And if we take some time to think about it, this would be our proton acceptor, and this would be our proton donor. Can we use that information to deduce the products? And it turns out we can. We get one hydronium ion, and we get a hydroxide ion as well. As you can see, the Bronsted-Lowry definition clearly shows what happens to that proton ion from an acid. You'll see that it associates with the water molecule to form a hydronium ion. And this is probably one of the better definitions out of the three, since we're going to be able to use this to apply it to bases. So, let's say we have NH3. And when we want it to react with, let's have it react with water. What would the products be for this one? So, let's think about this. Which one's the proton acceptor? Which one's the proton donor? It turns out that our water molecule ends up being the proton donor, and our NH3 ends up being the proton acceptor. And as a result, we get NH4 plus, and OH minus. And in the Bronsted-Lowry equation, the proton donors and acceptors tend to always occur together. And in this reaction, we got it down for bases, we got it down for acids, but what if there was more to it? What if we were to have, sorry, I got cut off, but let's say we have two equations to look out for. And you'll notice that they're the same thing. We've already solved them before, but pay attention to how water is treated. We end up having the following expressions, and let's see here, NH4 plus, and we have OH minus. You'll notice that water tends to play multiple roles. When it reacts with hydrochloric acid, it ends up being a proton acceptor. And when it reacts with NH3, it becomes the proton donor. In situations like these, molecules such as water tend to be amphoteric, where they can act as both acids or bases depending on the context. That's just something to point out when dealing with acid-base relationships under the Bronsted-Lowry definition. Now, what if we were to have this equation right here be reversed? What would that turn out? How would that turn out? You'll notice that it works the same way. It goes both ways, actually. So does that mean we need a double arrow? Yeah, of course. Now, quick disclaimer. You may be wondering, why does the bottom equation require a double arrow and the other one doesn't? Do keep in mind that when dealing with acid-base relationships, there are strong bases and strong acids, both of which tend to dissociate completely, meaning they break down to their individual elements. But for strong acids and bases, they don't dissociate completely, and in fact, some of the original reactant may still be present in the final reaction. So as a result, there's a matter of equilibrium. There's a matter of equilibrium when dealing with weak acids and bases. So that's just something to point out. Now, so far we were able to acquire the definition through the Arrhenius and Bronsted-Lowry method, but there's also more to the Bronsted-Lowry definition. So let's go back to our NH3 example, and what if we were to have it react with water? Well, we know that it ends up being NH4 plus, and we have a hydroxide ion, and we know for a fact that NH3 is our base, and water ends up being our acid. But what about the products? How are they defined? Are they actually defined? Well, in the Bronsted-Lowry definition, they are. So let's pay attention to our reactant NH3. Because it's a proton acceptor and it reacts with the acid, it gains a proton, which is NH4. And as a result, that ends up being defined as a conjugate acid. Now, what if we were to pay attention to water? With it being a proton donor, and looking at it post-reaction, it ends up being just OH minus. It lost a proton. And as a result, that can be defined as a conjugate base. So it ends up being that NH4 plus NH3 are referred to as a conjugate acid-base pair. What does that mean exactly? It's simply just two substances relate to each other by the transfer of a proton. And the same goes for H2O and hydroxide. So, a good, efficient way to understand this is to understand the following. That in an acid-base reaction, a base accepts a proton and becomes a conjugate acid. And an acid donates a proton and becomes a conjugate base. So, let's do a progress check. So far, we've defined the Arrhenius definition and the Bronsted-Lowry definition as well. Not only that, but we were able to identify which product is the base and which one is the acid, as well as their respective conjugates. Now, let's do a little bit of groundwork here. Let's say we have sulfuric acid, and we're going to have it react with water. Let's do some thinking here. Which one's the proton donor? Which one's the acceptor? If you figure one out, you pretty much figure out the other. So H2SO4 is one of the strong acids, and because of that, we know that it's a proton donor. So it's going to lose a proton, and it's going to lose a proton to the water molecule. So it ends up looking like this: HSO4 minus, and we have one hydronium ion right here. So we have defined sulfuric acid as the acid, and water is acting as a base in this situation. What are its conjugates? So a base that accepts a proton ends up being the conjugate acid. Okay. Now that we've revisited that, this would have to be, our hydronium ion would have to be the conjugate base. And an acid that loses a proton becomes a conjugate base. So we have that, and looks like I made an error. This should be, hydronium ion should be a conjugate acid. Sweet. So yeah, it looks like we were able to identify the elements within this reaction via the Bronsted-Lowry definition. Let's practice with one more chemical equation, where we have HCO3 minus, and we want to react with H2O. So HCO3 minus is not a strong acid, so it's going to require a double arrow. And let's identify which one's a base. Turns out HCO3 minus is our base, and therefore our water molecule will be behaving as an acid in this reaction. So that means we will have a hydroxide ion, and we'll have an H2CO3 CO3, yeah, that's it. Net charge is 0 in that element. So, okay. We have our acids and bases. Let's think about our conjugates. So HCO3 ends up gaining a proton. And because it gains a proton, H2CO3 is our conjugate acid. And our water molecule lost a proton. So this means the hydroxide ion is our conjugate base. Perfect. So in this video, we were able to define acid-base relationships via the Arrhenius definition and the Bronsted-Lowry definition. And you'll notice that one's much more applicable than the other. It's beyond identifying your acids and bases, but also deducing the identity of its conjugates. I hope this video helps, and if you have any questions or concerns, please feel free to drop in the comments.